Hi, this is Scott Wilkinson, host of Home Theater Geeks. In episode 338, I chat with Rod Sterling, JVC's chief engineer, about projection technology. So stay tuned.
Netcasts you love.
From people you trust.
This is Twit.
Bandwidth for Home Theater Geeks is provided by CacheFly at CacheFly.com. Hi, this is Leo Laporte, and once again, time for Twit's audience survey. We'd really like to hear from you. It's only going to take a couple of minutes, really. That's all. Just go to twit.tv/survey and let us know what you think. Your anonymous feedback will help us make Twit even better. And thanks for your continued support.
This is Home Theater Geeks with Scott Wilkinson, recorded January 26, 2017. Episode 338, all about JVC Projectors. This episode of Home Theater Geeks is brought to you by Grasshopper. Stay connected and run your business from your mobile phone with Grasshopper. To save $50 on your order, visit trygrasshopper.com/twit. Hey there, Scott Wilkinson here, the Home Theater Geek and editor of avsforum.com. This week's guest geek is Rod Sterling, chief engineer at JVC. Hey Rod, welcome to the show.
Greetings, everyone. My first initiation into this, so I hope we have a great time.
I'm sure we will. I will treat you gently, I promise. Before we get going, I want to make sure that everybody knows that those who are watching live at live.twit.tv can join the chat room there, or at irc.twit.tv. And I will be looking for questions. You can post questions there, and I'll pass along as many as I can. It always helps if you put my screen name in the question anywhere in the message. My screen name is Scott Wilkinson, all one word, no dots or dashes, because that way it shows up in a different color on my screen. I also want to let all of our Twit fans know that we want to hear from you in our new audience survey. It should only take a couple minutes to finish, and it will give us a general idea of who our audience is, and it will also let us provide better programming and select advertisers you'd be interested in hearing about. Of course, many of you take privacy very seriously, as we do, and we promise to always protect that. We do not identify you in any way in the survey. So head on over to twit.tv/survey now, well, after the show, and we thank you very much for your input. Okay, so Rod Sterling, you are the chief engineer at JVC, and specifically Projectors. JVC is a huge company, and they make a lot of different products. You're involved in Projectors, right?
That's correct. I've been doing this about 33 years, so I've seen a few of them come through the pipeline here.
Well, let's start with a little bit of history, because JVC, this particular type of projector technology, which we're going to dig deeply into, got started, I believe, with Hughes, the aircraft company, right?
Yes, we have our roots in aerospace, and it's still one of our good business sections. But the original work was done with Hughes and liquid crystals and different ways of modulating liquid crystals. But it wasn't until we actually did a joint venture and merged with JVC that we actually made this available to the home market, which a lot of you out there are very aware of, the quality and the performance of our home theater products.
Oh, yeah, no question about it. I mean, JVC home theater projectors are invariably considered among the very top of what one can get in the home because of the high native contrast ratio, deep blacks. There are many factors that really make JVC projectors very desirable to home theater people. Let's take a little look at the history of how it developed over time. And we have a graphic here called D-ILA Projector Timeline. So you can sort of take us by the hand and lead us through this this development process. That's a lot of projectors over a long time.
Yeah, this started back in '97 here. But you can see that one of the key reasons JVC has been successful is we own the core technology, and that's the D-ILA imaging device, generically known as LCoS. And you can see different families of projectors derived as the devices are developed into new higher performance devices. So we'll make a lineup off of each device as you go along there. But it's really the device side itself that allows us to make these quantum improvement. I wouldn't say quantum, but we have small little steps and big steps, and it's usually when we change devices. Yeah. So evolutionary versus revolutionary.
Right. And sometimes the steps are one and sometimes they're the other. Remind us of what LCoS and D-ILA stand for.
The term LCoS is generically known as liquid crystal on silicon. So that's the LC is liquid crystal on silicon, the S. So that's liquid crystal on silicon. D-ILA is direct drive image light amplifier. So that was the marketing name chosen to differentiate it from other LCoS.
But it's basically the same technology, roughly.
On paper, yeah. The know-how in how you build the backplanes, process the rest of the device, and manage the liquid crystal is the secret sauce, so to speak, that is unique to different manufacturers.
But in the case of LCoS and D-ILA, basically a light hits the imaging chip, passes through a liquid crystal layer, bounces off a sort of a reflective surface behind it, passes through the liquid crystal layer again, and each little pixel lets more or less light pass through, which gives you your image. Have I got that right?
Yes, there's one very important thing that you didn't mention, and it uses polarized light. So the liquid crystal actually rotates the polarization is how you get that. And that's what gives us the great contrast ratio. You can't do that with basic mirrors reflecting off at different angles. By doing the liquid crystal, we actually rotate that. And with the advent of wire grid polarizers and other features incorporated over the timeline that you saw there, we've been able to get extremely high native contrast ratio from the HD1 forward when the products went to the wire grid technology. So there you had another technology that was developed along the way that added improved performance. So the native D-ILA itself was very good contrast, but we had to improve the optics to allow us to show the maximum potential of the device. And so that was another improvement along the way that allowed that to happen. If you don't use polarized light, it's harder to get over a few thousand to one contrast that you've seen in other types of technology.
And we should distinguish between native contrast and dynamic contrast. So tell us the difference between those two.
Yeah, it's as you go through time, you have a lot of words like brightness and contrast and different ways of doing it. Then later on, because the basic fundamental devices out there modulating the light had a limitation on contrast, so you had people get clever. How can we get a better black and still within the realm of the contrast of the devices we have? So they came up with this approach where you actually dim the light going to the device. So you can do that with apertures, and later on now with LED and laser, you can dim the light source. The problem is you still fundamentally can only, let's say it's a 2,000 to 1 contrast ratio. You still have 2,000 to 1, no matter how bright the image is. You can have full brightness or 1/10 brightness, and you still can only go from 10th brightness, 2,000 to 1 up from that, or 100% brightness down to 2000 to 1. So you're limited to what it looks like. So even though you can get very good black levels this way, the whites aren't very bright because you only have that dynamic range to deal with. Where if you have a native contrast ratio, that is whatever the light intensity, you go from the black to the white. And in our case, it's 50, 100,000 to 1. So it's a huge difference. And what it does is if you're looking at star scenes or highlighted details, now that we're starting to see in this new HDR, which we'll get into later, the wider dynamic range gives you much better performance and look much more realistic looking.
Mm-hmm. I think in particular, I generally don't like dynamic contrast, which, as you say, is either an iris or making the laser or LED brighter or dimmer. But when you get a scene with some dark parts in it and some really bright parts in it, you can't render them both accurately. One of them is going to suffer. But if you have native,
it looks flat.
It looks flat. But if you have a really high native contrast where you can just leave the light on at a given intensity and keep it there, and you still get a wide dynamic range between black and white, that's a much better situation. And that's one of the things that the JVC projectors have always been known for, and why they're so well received in the enthusiast community.
Right. And we continue to improve that every year. We part of it's in the device and the other parts are in the optics. So if you notice, every year we have a new model and it gets a little bit better each year. Sometimes it gets a whole lot better.
Yeah, just at CES a couple weeks ago, we saw the latest iteration of the consumer products. I have to ask you this, though. JVC makes it a little difficult for journalists such as myself to write about these products because you have two distribution channels. And I don't normally talk about distribution channels on this show, but in this particular case, it's a little frustrating because you've got the reference series and you've got the Procision series. They have different model numbers, but they're exactly the same projector.
Yes.
and I know you're not a marketing guy, so you probably might not know the answer to this, but why in the heck do you do that?
I guess ask General Motors how come they have a GMC pickup and a Chevrolet pickup.
Okay. All right.
Scenario. That's the best correlation I can see from. If they put them together, they'd be the #1 selling in the world. But as it is, they get outsold by Ford every year because they got two models. That's something to ask a marketing person. There's definitely some advantages of having distribution channels, versus the other. If they start putting dollar signs in front of things, I don't talk about them. Anything but a dollar sign.
Normally, I don't either. That's exactly right. Other than retail prices, I guess the general rule is the reference series is what consumers can buy directly, and the Procision series is what custom installers might get and use and put in a home theater that they're building custom.
It's actually the other way around.
It is the other way around. Okay, sorry. Procision is what people can.
They buy those through dealers out there in most cases, and then the reference series is typically sold through distribution. So
gotcha. All right. Well, let's get away from marketing because that's not really what this show is about. I wanted to talk a little bit about the difference between the different types of imaging systems that are used in home theater projectors these days. And we've talked about D-ILA, which is a variation of LCoS. There's also DLP, which generally is found either in really inexpensive or really expensive projectors. Not much in the middle anymore. It used to be a little bit. And then there's LCD. And we actually have a graphic that shows a little bit of the difference called imager comparison. So let's take a look at that while you teach us a little bit about the differences between these different technologies.
Okay, so LCD's probably been around the longest, at least in the digital form. As we mentioned earlier, we had in the Hughes days, liquid crystal modulators, but they were not digital. They were analog based. But along came LCD, and I think back in the mid to early 90s is when it first started coming, and you had some people that were taking these view graph things and putting them in a bigger lamp and making projectors out of them. And everyone said LCD was going away, and it just keeps getting stronger. So it's had a long life, and it continues to do that. The thing with LCD is a transmissive device. So its biggest drawback is because it is transmissive, you still need some room for a transistor to rotate the liquid crystal. So it basically, instead of, we mentioned earlier, reflecting, it actually, the light goes through the back and comes out the front, and you rotate it. You still need polarizers to extinguish the light or turn it on. But as the light goes through there, you polarize it, rotate it, and it comes out an analyzer. So you have cross polarizers, polarizer analyzer with the liquid crystal in the middle, and that gives you the performance. And again, the aperture is limited because you have some of the transistor circuitry required to move the liquid crystal or rotate it to give you the image.
And so that transistor actually takes up some of the space that the light would otherwise go through. So it reduces the amount of light that actually gets through because it's blocked by these transistors, right?
Right. And it's not all blocked. Some of it's absorbed, which means it turns into heat. So there is some power limitations that you can go to also, because you have to dissipate that heat, and the transistors on glass, because it's transmissive, and glass isn't the best conductor of thermal energy. So you have some power limitations. You have the transistor in the way. But when you go on projectors, you can see that because they're usually in the order of a 1 inch or 1.5 inch chip size. But you go to LCD panels now that are getting into the 100 inches or better.
You're talking about LCD TVs now.
Right. Now you've got a very big transistor in the liquid crystal cell, but the transistor is still about the same size. So as you get into these great big TVs, the transistor is less of an issue. And so you can, they do a very good job on looking at 40, 50, 70, 100-inch type displays and bigger now. The other thing you can do is now they've gotten better at putting lights behind those so you can get a higher dynamic range. Again, they were limited to a couple thousand because of the way they worked. So that's basically the LCD. The core difference between it and the other two modulation, the imagers, it's the transmissive display.
Right. Light has to transmit through something, an LCD layer in this case.
And you can use various light source. The old ones were cold cathodes. So you've got LEDs now. You've got quantum dots.
And again, this is for flat panels.
For flat panel. Now for projectors, you've seen they were the early adopters of the laser-phosphor technology because it worked well. The optical layout's fairly straightforward with these. And so you saw some of that coming on. There's been some implementation of LEDs, but the laser still works, gives it the best performance. And so we see some of these, and even in the small little business ones, you can see those out there on the street.
Right.
Now, if we go back to the graphic, we can probably look at the other.
Yeah, well, let's take a look at the other two here. By the way, before we continue, let's define the term aperture ratio.
Okay, aperture ratio is, let's just say you have a square pixel. Now, a pixel is something that will have light. And in the old days, you had a CRT, which was an emissive display, and that pixel was Gaussian shaped, and it emitted light. Now, when we go into imagers that we're doing here, a good example would be a screen door, where you have little squares in it with little black lines around it. So if you look
around each square,
away from it, if you look away from the screen doorways, you see through it, and it just looks all attenuated a little because of the wires blocking some of the light.
Right.
And that's what happens when you draw a pixel. If the old analog devices actually did have pixels in it, they were very smooth and no lines. But when we went to digital, you have to turn each pixel on individually. So you must be able to control them individually. To do that, you got to draw lines around them and make them independent of each other, or you have no resolution. So as we put a line around the pixel, how small can you make that line, and how large can you make the area that doesn't have the line is the aperture ratio. So 100% aperture ratio, the line would be 0, and you'd have 100% of the area lit up. So if you go to a 90%, 10% of the area is now the line around the device, and some of that could be transistor too. It's the ratio of the light to the theoretical limit to the actual limit. So if you have anything blocking that 100%, it goes below 1, and therefore we get the 50 to 65% aperture on the LCD. Now they're up to around 90, 91% on the DLP, as you can see in the graphic.
Mm-hmm.
So
DLP,
they've gotten better.
They have gotten better, certainly, and even LCD, I think, has gotten somewhat better over time.
Yeah, this slide is an old one. I apologize for that, but it had the best graphic that I had in my toolbox. So it's about 7 years old, so it has gotten better. But the other problem is you go to smaller pixels. As I mentioned before, with the large LCD TVs, those are 70, 100 inches. You have a lot of room. The pixel size for an HD or even quad HD display is still quite large. If you're talking a projector with something around a 0.7, 0.5 inch device, if you put 8 million pixels on there, there's so much room. The lithography used in creating these has to have a certain amount of lines, the pitch of it, they call it.
Right.
And because of that, as you get more pixels on there, your aperture ratio starts falling off again. Just because the lines, imagine a pencil, you can only sharpen it so fine. And if you draw that box, that's what you end up with. So as lithography has gotten better over time, you've seen aperture ratios go up, and then you see, well, we want 4 times more pixels. So then it kind of drops back down, and then the lithography guys sneak back up on it. So it's a constant chase. So, one guy how small can you make your line, and the other guy saying, I want more pixels. So,
right. Constant battle there.
Historically, the LCoS has always been the best aperture ratio because it is flat and you can draw the lines. And the mirrors, you still have to move them. And there's a lot of mechanics under there. It's not just drawing a line around a pixel. There's the circuitry as well. Now, the advantage of DLP... go ahead.
I just wanted to mention that DLP basically relies on millions of tiny little mirrors on mechanical pivots, and they pivot between one position and another. We could see that in that graphic. In one position, the light is reflected away from the lens, and in another, it's reflected towards the lens or towards the screen. And this always amazed me because they are, microscopic little mirrors on even tinier little pivots, and they go back and forth really fast. So I just wanted to make sure we understood that.
They're actually small enough. They're actually a silicon hinge or like a spring. And if you get small enough, it lasts for a very long time. It's not like a paper clip where you bend it 20, 30 times, it breaks off. So they're down at the smallness level. You're in a different kind of physics. So they really don't break off on you, so to speak. They do last a while.
Yeah.
But
the mirrors can be put pretty close together with very little space between them, which is why you get an aperture ratio of over 90%, right?
Right. Now, what limits them, and in the last 5-6 years. I can't remember the date when it came out, but they actually improved the device where they rotated the mirror more, because that's what is limiting the contrast. Because you have a light coming in, you rotate it off, and you got to trap the light to give you your contrast ratio. So you can either shine it on or shine it off. But if you shine it off somewhere, your lens has to be able to not capture the off light. And so as they improved,
that light's got to go somewhere.
Yeah. So as they went from 1,000 to 1 to 2,000 to 1 in the cinema world, part of that was the amount of tilt they were able to add to that. And they can be very fast, so they can do things with single chips and things like that. Mm-hmm. But again, the circuitry's under the mirror, so you get the very fine aperture. So your drive circuitry, and the same with the LCoS, is underneath the pixel. So that gives you only the line width to worry about, where the LCD has the line width plus the transistor in the way, because you can't hide the transistor. I don't think they figured out how to put the transistor in the line yet, but somebody's clever, maybe they will. But right now, it's the big difference between LCD, DLP, and LCoS is the transmissive one still has to. You still see the transistor. If you look up real close on it, you can see a little dot in the corner. If you get your magnifying glass out, even on the big TVs. So.
Right. Another thing I wanted to make sure we talked about. Well, let me ask you this. You mentioned resolution, and we had HD high definition 1080p for a while. Now it's UHD, ultra high definition, or 2160p, 3840 by 2160, 4 times as many pixels. They have to be smaller, and so you get this conflict between the lithographers and the resolution folks. And one way that JVC has chosen to maybe address this issue is with a technology you call eShift. Mm-hmm. So I'd love for you to explain to us how eShift works.
This has actually been around for quite a while. Hewlett-Packard did some of the original patents on this, and even before that, they used this same type of approach in cameras to get more resolution out of it. We actually implemented it in our home products. I think it's 8 or 9 years now. So we've been at it the longest. We see a couple more people now starting to utilize that same technology, as we don't have it locked up any longer.
Mm-hmm. There are other companies that use a similar technique. That's true.
I think we have a graphic on there.
We do. We have 4, actually. eShift 1. Let's start with eShift 1. So
what the shift does is and you can do different types of elements in there. I won't get into that, but basically you put an optical element in front of the imager, and it's designed such that when you apply a signal to it, it shifts the pixel, the image of the pixel, over half a pixel and down half a pixel. And that's kind of like looking through a fish bowl. If you look at you stick a pole in a fish tank, and you'll see that the pole looks like it's shifted over partway. It's the same type of effect where the pixel is actually shifted.
It's light going through 2 different media, and the speed of light changes when it goes, say, from air to water or air to glass. And if you put like you say, you put a pencil or a stick or something in a fishbowl, it looks like there's a bend in the stick. And that's only because the way light behaves in the 2 different media.
Correct. So by putting this element in front of there, and the ability to switch it at double the frame rate. So in this case, we switch 120 hertz on a 60. And we effectively now have another a spatial difference in our same imager. So if we run the imager twice as fast, so 120 instead of 60 hertz, and then we shift the image, we actually can put up 2 pieces of data that are spatially different. So what that allows you to do,
but they overlap, and that always kind of concerned me, because wouldn't that tend to soften the image, maybe? I mean, as opposed to an actual true native 4K imager, you've got these 2 pixels, and they can be addressed separately, and you can have different content, different information going to each one, but they overlap, and I always wondered about that.
Well, if you talk about a native 4K, yes, the native will be better, but this is much better. It's like twice as good as an HD, where a native would be 4 times. So if you think of it as bandwidth, we're able to put up twice as much information, not 4 times as much information, because you have double horizontal, double vertical.
Right.
And one of the big advantages of eShift is it eliminates the pixel structure, or it removes it to almost 0.
Oh, that's a good point.
If you get up and look real close, it depixelizes a pixelized image. So it makes it very smooth and natural looking. So by that, having that overlap, you do not see that discrete pixel, which you can see on a lot of the technologies out there. Even at 85-90% aperture, you still see pixel structure. With the eShift, that really helps eliminate that.
Now you have we have some other pictures. I'm sorry, go ahead.
I was going to say, let's go to the next image.
Exactly, eShift 2.
So the other thing, if you remember, a lot of this data was taken in our simulation world, where we have better control of things. So these models here were, there was equivalent models in the commercial world, but this is basically some work done on the eShift. So on a normal non-eShifted projector, let's say in this case we had a native HD, and the MTF is a measure of resolution. Now,
our MTF stands for
modulation transfer function. Okay. And it's a normalized value, so it's always 0 to 1. So no matter how good the resolution is, it's still 0 to 1 in this transfer function.
So this transfer function, how does it indicate resolution?
It basically is the measurement of contrast between a black and white alternating lines. So you would put up 2 pixels on, 2 pixels off, 3 pixels on, 3 pixels off, and you measure with a precision instrument the actual brightness between the black and the white. And that ratio between black and white is normalized to give you a modulation number. So if the whole image was white and then you turn the whole image off as black, that gives you your 1. So that gives you the reference to what black to white is. So it's independent of contrast in that sense, that it's normalized out. So it's really trying to measure how well you modulate a white and a black line. And if you go get your eyes checked, they have a lot of tests up there on the chart with these little lines at different contrasts to see that. And that's basically the same thing here. But as you get to so all lenses have some MTF or resolution, and there's other components in the optical system. But as you have a fixed matrix, let's say an HD imager, as you get out to the 1920-2160, if you want to do 1921, there's no pixel there. So you basically fall to 0 because there's no modulation once you're out of pixels.
Okay, so that's in high definition, 1920 by 1080. If you are alternating white, black, white, black, white, black each pixel, you get to, if you try to do 1921, there won't be anything there.
Right. That's a simplistic way of putting it. Then you put scalars and different things, and you can get some aliasing, and you can stretch it out. But basically, you can put 2 on, 2 off, 3 on, 3 off, 1 on, 1 off, but you can't do, when you run out of that, you can't go below 1, let's say.
Right.
Now, with the eShift, you can go below 1 because that element is shifted halfway over. Now, you are spatially dithering or temporally dithering these, so you do have a, like a pixel interlaced image, but where the one image is and the next one, there's no line there, you can actually put one there. So it does improve it. And if you look at this curve, this is a measurement at I think you can read the 0.5 or 50% limit there at the Nyquist limit. You basically, in a regular system, you can't resolve anything much beyond that limit. And so the area under that curve is not really usable or readable for various reasons in a HD projector. I think if we go to the next slide, with the E-shift on, you've doubled the input, the bandwidth coming in, and you can actually resolve it. But it's not, as you mentioned, if it was a 4K, it would be up around the 60% mark because the lens rolls off and the optics, you never get the 100, but it would be high. Mm-hmm. Because this is shifted, you actually get a very CRT-like looking or film-looking type approach. You can still resolve images out close to the 4K limit, but it's only 3 or 5%. If you go out to maybe 3,000 lines, you're up around 75% 0.3 modulation. You're out around. So let's see, 3,000 lines on 4. Yeah, it's around 75%. So you'd be up around 25-30% modulation at 3,000 lines. You put 3,000 lines on a HD chip that you don't see it. Yeah, so it does enhance the resolution. The most visible thing you notice is it makes circles round and makes lines straight.
Without having jaggies in them, you mean?
Right. So that's the most visible difference. So again, what's your viewing distance? How's your room set up? A lot of times, if you're at about the same viewing distance, it's very difficult to see much improvement because you approach what's called eye limiting. And if you remember a few years ago, there was a big discussion on 720p versus 1080. Why do you even need this? 10, 15 years ago, there was discussion on the theaters because the first digital cinema was 1,000 line resolution, or the chips were 1280. They weren't even HD. Now they went to HD. Then now we have 4K.
Right.
But most theaters are still 2K with a lot of good glass in between it, but they still look fairly good. It's by adding this E-shift, you can get rid of the distraction of the pixels, which personally drives me crazy. And it smooths out the image to a much more natural scene. Now, it doesn't look as sharp because part of the sharpness we perceive is the lines on the pixel. But when you look in the real world, you don't see those lines unless you're looking out your screen door.
Which I try not to do.
Yes. So it gives a very natural, realistic look. You've got modulation below 50%, which you normally don't have in a digital projector because it falls off there. Mm-hmm. And in real world, you have modulation from 0 to 100%. So you can you perceive it more natural.
Mm-hmm. One last slide before we leave this topic, and that is you mentioned the effect of glass on the modulation transfer function. And here's an example of that. Tell us what we're looking at here.
Okay, so this is kind of back to what you said. Here's the native 4K, is the purple line on the top. And the yellow line on the bottom is the actual measured E-shifted projector. The green line in the middle is the theoretical one. But the actual one versus theoretical has to do with the lens performance. So the difference between the green and the yellow is the effect of the lens and how it falls off. And so the E-shift, if you go to there's a red line in there too that's right on top of the yellow until you get to the 50% point. And then it goes to 0 because that's all, you can only resolve 1920 pixels. So
I see. Yeah. That the horizontal, the vertical white line below the yellow line becomes red because it falls off very steeply right there, completely.
That's why we put the red dot, so you can follow the HD. So with the lens and that, it follows the E-shift projector until you get to the 50%. Then it goes away, and you have all the other resolution there that's available to perceive, to view in the image.
Mm-hmm.
But again, you go back to the native 4K. Of course, it's got twice as many pixels. Again, it's 4 times HD.
Yeah.
But even at the limit, it's not 100% because you have lens effects, you have crosstalk in the pixels. There's, a lot of other effects. So you never have 100% all the way across.
Right.
But you can see how it's better than HD by a ways. It's not as good as native. But if you're standing back far enough and you can't resolve more than 3,000 lines, it's going to be hard to tell them apart.
Yeah.
Most people that see the difference are up looking at the screen and not back watching your movie. So it's a good low cost, lower cost approach than the true native projector is.
Mm-hmm.
And it still puts up a very good image because there's a lot more to an image than just resolution. You have the color, the contrast that we talked about. A lot of these other aspects can add to the image greatly. You can have a very high resolution image that looks very poor.
Right.
And it's not just one piece of the total image.
Exactly. Well, we've got a lot more to talk about, but before we do, I'd like to take a moment to thank our sponsor for this episode, which is Grasshopper. Now, Grasshopper is a virtual phone system designed for entrepreneurs. Grasshopper works just like a traditional phone system, but it requires no hardware purchase. With their iOS and Android app, callers can reach you wherever you are on your mobile phone. Grasshopper allows you to keep your existing number so you can maintain your brand. When you make a call, your client will see your Grasshopper caller ID instead of your personal phone number. Simply select a toll-free or local number, record a custom greeting, and add multiple extensions for your business. Toll-free numbers are great for marketing and make your business sound much more professional. You can set up department and employee extensions with custom call forwarding to any phone in the world. You can also get voicemails emailed to you as audio attachments. And you can send and receive SMS text messages from your business number. So join the over 250,000 Grasshopper customers today. Plans start at just $12 a month, and you have a 30-day money-back guarantee. Turn your smartphone into a business line with Grasshopper. To save $50 on your order, go to trygrasshopper.com/twit. That's trygrasshopper.com/twit. And we thank Grasshopper very much for their support of Home Theater Geeks. So I'm talking with Rod Sterling. He's the chief engineer at JVC, and we're getting deep into projector technology here. I think we've got a couple of questions in the chat room here. Mike Heiss is in the chat room, my good friend and a regular guest on the show. And he's asking about eShift. Can you do that with 4K imagers to get to pseudo 8K?
We've had that product for a while now. It's mostly used in fast jet military applications. Home is struggling to get to 4K right now. When it's available in 8K soon, yes, you can eShift an 4K to get the 8K. And that model's been out maybe 3 years now, I think. So, okay. It does a very good job. We've demonstrated it several times at the ITSIC trade show. It's a military simulation trade show in Orlando every year. And, it does a great job.
Emily the Strange has made a very good point. This e-shifting is sort of like anti-aliasing.
It does a very good job of cleaning up aliasing problems. That's one reason they like it in the simulation world. You can take an image generator that has a lot of aliasing problems. You put that into an eShift projector, and it cleans up a lot of that. It causes some other problems, but nothing's free, But it definitely
Nothing
helps.
is free, exactly.
You just keep peeling the artichoke back. Yeah, it is. It's good. You depixelize. It also covers up the aliasing mode, so it's a very good observation there.
Yeah, thank you, Emily the Strange. She was afraid she wasn't going to understand today's show, but no, she gets it very well.
You got it quick.
Yeah. Let's take a look at some light sources. You mentioned, and we know that in most home theater projectors, up till now anyway, have used a big white hot lamp. But more lately, we've seen some laser illumination. We've seen LED illumination, and in particular, I'm interested in the type. There's couple different types of laser illumination. One is RGB, where you have a red, a green, and a blue laser for each of the three colors, but that's very expensive. So instead, I've seen many times the use of what's called blue pumped phosphor or blue laser yellow phosphor, which is what JVC and many other companies use in your projectors. I mean. So tell us a little bit about blue pumped phosphor while we look at laser illumination.
Okay, I do want to digress. When I first started in the industry, I actually ran a carbon arc drive-in theater. So that was
really?
Even back before the lamps. Yeah, that was fun.
Oh, man.
So let's go back to the schematic we had up there. The LED is nice, but it has brightness limitations. And one of our goals to get costs down is to make imagers smaller and smaller, even though we want to shove more pixels in them. The smaller the imager, the lower cost you can make it. So there's a little term in optics called étendue, and it basically means how much light you can collect onto a given area. So as the imagers get smaller, you can collect less light on them for the same étendue. Now, one advantage of a laser, the étendue is very good. So it's a beautiful matchup for like LCoS projectors and that, because we can collect a lot of light into a very small imager.
And the laser produces an awful lot of light.
Right. And if we go back and thank the people that developed the Blu-ray disc player, we can thank them for this, because all that early development on getting the right magic to work, the chemicals and working it out to get the good blue lasers at a low cost, as that was the key, is getting the costs down. Now, so we use a blue laser block. This is a schematic of the simulation model. Our home model uses a different, there's more than one laser phosphor method. I think on our website, I have a couple white papers on both of them. But this concept is the same. You have a blue laser, you image that onto phosphors. Can either be a wheel to cool, or you can have a phosphor solid on a ceramic and cool that, and it will emit a yellow light. And in some ways, this is the same as the old CRT days, where we had the YAG phosphor, we hit it with an E-beam, and we got a red or a yellow, a red or a green light. This is the same type of phosphor back from the CRT days.
Wow, what's old is new again, huh?
What's old is new again. And we hit that with the blue light, we get yellow light out. And depending on the ratio of that, we can make a nice white light. Then we can run that.
Because blue plus yellow equals white.
Correct. And there's other ones out there, but this is the one that's really caught the traction. There was some green ones and red ones, and you had different early adopters of these LCDs were trying different phosphor combinations, but the one that has the lifetime and the brightness and that is really kind of settled into the blue laser with the yellow output. Now, some people say it's white output because the blue goes in and it comes out and it's blue and yellow and it really looks white, but it's still the only part that's laser is blue.
Is blue.
But we combine that. Yeah, go ahead.
I was going to say, I Am Special is asking the question, where does green come from? And I think you were about to answer that question.
Right. So if we go back to the little graphic again, we still come in. From this point on, we treat it very similar to we did with the lamp, because the lamp had white light coming in. And a lot of our projectors had the same chassis that we just end up using a laser phosphor source instead of a lamp source. So you come in, you split it into still the red, blue, green elements, and then each of those are imaged onto our D-ILA devices and recombined back out to give the color. So that way you can control the red, the blue, the green, and do your color mixing so that you get the right color primaries and things like that. And so for wider color gamuts, you have to trim off some of the yellow and orange in there to give you the DCI color space and things like that. This is the blue is very narrow band, but the yellow is still broadband. So we still have to trim that with our dichroics.
Right. And I should make sure that everybody understands that basically when you combine blue and yellow, you get white. And from white, you can extract red, green, and blue. Another way to look at it is yellow light is actually composed of a combination of red and green. So you can separate the yellow light, if you wanted to ahead of time, into red and green. And actually that leads to a question, which is does anybody ever do that? Take the yellow light from the phosphor and separate it directly into red and green without going through a white stage?
There's one problem. There's different layouts. I won't say no one's doing it, but when you hit the laser onto the phosphor, there's still some yellow or still some blue light coming out. I think you'd want to clean that up a little bit. Mm-hmm. In our second gen, you have the blue and yellow coming out together, so that would not work at all on that one. Because the blue light is reflected off of the disc. Some is absorbed, but the other is reflected. So
right.
If you want the pure color, you would need to still clean up the residual blue left in there.
Mm-hmm. SoCal Ray Jr. is asking, what is laser light engine life expectancy? Oh, you know what? We're going to talk about that in a minute. So hang on, SoCal Ray Jr. We'll be right there.
Okay.
So go ahead. Sorry to interrupt.
I didn't know where you wanted to move into the RGB lasers or not, but
well, you know, I would just mention that's another way to do it, but it's much more expensive, isn't it?
Yeah, right now, particularly the green. The green's the hard one, but there in that system you can go direct to the imager, red, blue, green, because they're all pure color. You don't need some of the other dichroic elements in there. Mm-hmm. Unless you want it for simplicity of layout or something. But there you can actually drive each imager with the red, the blue, the green. Now you'll see that in the big, 60,000 lumen theaters. You're seeing some of these manufacturers that are using pure laser now, and they use a lot of them. But it's another way to get wide color gamut, which we may touch on a bit too. If you ever want to get to the Rec 2020, you have to get out to a laser to be narrow enough to get out there and still have any light left out of your light source. So there's some advantages. There's also a big speckle contribution there that you have to deal with. People are getting clever. There's new materials coming around. So the speckle's starting to get under control some. Again, nothing's free. You do one thing, you find some other problem. You got to engineer around it. But I'm not going to try and forecast when those will be at home, but they are commercially available in the cinemas now. So
sure.
You can imagine that would eventually go home.
Yeah. IMAX and Dolby Vision, Dolby Cinemas, both have RGB laser illuminated projectors, but those are really, really expensive. Before we get to SoCal Ray Jr.'s question, Sentinel is asking, can quantum dots be used as a light source? That was one of the questions I had for you as well.
Well, quantum dots are tied in with LEDs, and they control the wavelengths. OLED might be an interesting one, but again, it's suffering brightness. The problem is these work on 60, 70-inch displays, but trying to project them through an optical system with its losses and that, I won't say they can't be. There may be a laser quantum dot combination, which I'm not sure makes sense. I think it's a little early. Quantum dots are just getting their traction now in the LCDs, and they're still struggling. But we're seeing big improvements this year at CES. You saw a lot better implementation with quantum dots by the majors. I won't say no. I think it'll be a few years. The laser seems to be a much more compact and easier way to go, probably in the next 5 years anyway.
So let's talk about life expectancy. SoCal Ray Jr. Asked about that, and we have laser lifespan, I think was the name of the graphic. And so we can take a look at that, and you can tell us about that as soon as we see it. Laser lifespan. There it is.
Again, I look at my correlation on lasers. A good friend of mine in the optics world, and I've used his term from then on, is think of a laser as a photon bucket, and you can pour it out, and the photons will go until you run out of photons. So that's the lifetime. So if you drive it really hard, 100% all the time, you'll run out of photons earlier than you will if you use them at half that rate. What most manufacturers are doing is assuming you run at full power because you can't really tell how a customer wants to use his product. And so we typically quote in the 20,000 hour. And that's just strictly limited because of the laser diodes. And it's a thermal issue. It's how many photons you can get out of that until you get to about half the brightness. So they'll keep running. They'll just won't be as bright. The phos, a lot of people ask, well, what's the phosphor? It's going to burn up in that. Phosphor is like 100,000 hours. So the burn down on a phosphor is a whole lot less than that. But at 20,000 hours using full power all the time, that's quite a bit better than you're getting on lamps. That's like 5 years of a 4,000 hour lamp. So plus you don't have the up and down beats. Now, if you run it a little less power, then you can get into the 40, 50,000 range. So again, don't pour all of your photons out at one time and kind of throttle them back a little bit. And the nice thing about these projectors, they have enough brightness now with these, you can actually still get your 16-foot Lamberts on the screen, or 14, or some people like 20, whatever, and still have some headroom left so that you can get a longer life. And it's much more stable this way too. You don't have the lamp that's burning down quickly at the beginning and then tailoring off and doing its different thing. So it's definitely, you've added 5 to 10 years. So you're going to be changing your projector out long before the laser is going to wear out on you.
Well, let's take a quick look at the RS4500, which is JVC laser phosphor projector, illuminated projector with true 4K. Now, this is not eShift. This is an actual 4K imager with a blue laser yellow phosphor light source.
So this product is kind of an evolutionary product where it is our first native 4K in the home. We've been building 4K projectors since 2000, but used mostly in military applications or command and control things where you needed 4K, but it wasn't home priced. This has a new 0.69-inch native 4K imager, a D-ILA. It also is our first introduction for the laser phosphor, or what we call blue essence, our trademark on the laser phosphor. And it's our first introduction to the home with that. We've had it for 2-3 years now in the simulation, commercial simulation market. So this brings in the new light source technology, a brand new imager, a native 4K for the home. So it adds a lot of features, and it's probably one of the best boxes out there to do the new HDR standards, because it does do a quite nice job with the native contrast and the other features you get, with the D-ILA and the circuitry we've got in here now to handle the HDR content.
Which I do want to spend a few minutes talking about, but before we do, I wanted to take a quick look at the color gamut of the RS4500, which is the next slide, I think, and that will show us the sort of range of colors that the blue, laser, phosphor, yellow phosphor light engine produces as compared to some other ones. Tell us what we're looking at here. Okay,
we started out talking about HD and the color gamut, and gamut means the red, blue, green primaries. How deep a saturation can you get in a pure green, a pure red, a pure blue?
Which are the points of the triangles we're looking at here.
Right. So the green is green, the blue is blue, the red is red. Okay. So HD, it's standardized on what we call 709 color. So your HD TV sets, HD movies, the early those are mastered for the home. Were done at the 709 color,
which is the green triangle here, the smallest.
The
triangle.
Smallest, yeah. So that'd be the max or the most saturated color you could get. Then with the advent of 4K, well, let's back up again. When the movie theater came out and they wanted to go to a digital format, but they didn't want to be limited to HD colors because film was much broader, they created a standard called DCI, or Digital Cinema Initiative. Some of the early Texas Instruments stuff called that P3 or P5. But basically, that's the color gamut used in digital cinema.
And we can see that the colors are particularly the green is somewhat more saturated, the red too.
Yeah, the blue's about the same, but you get deeper reds and definitely much more saturated greens, which means your yellows move up, your oranges move up, so you get more colors in the secondary world. The next red triangle is what the RS4500 is. So it exceeds the DCI. So when you actually color to a DCI, you have the headroom to bring in the colors and nail the DCI color spec. Now, the blue triangle is BT 2020. Can we do that with this unit? Yes, but you'd probably have about 50 lumens or 100 lumens out of it. That's why I say you got to go to lasers. The laser needs to be on those points to get all the light out, because otherwise it's so narrow that any other illumination has a hard time meeting it. And it's still, the true 2020 is, there's still work needs to be done on getting the tools to master to a true 2020. Mm-hmm. So what people normally do is they color map into either 709 or P3, because those are something we can do today. And so when you look at a true HDR movie that has the BT 2020, we're mapping into a little smaller gamut, but it's mapped so that you do see much better saturated colors than you did on the old Blu-ray type movies that you were watching.
Mm-hmm. F-Loop in the chat room is asking, does metameric failure become a real problem with laser light, or is it just theoretical? And we should explain what that is.
It's very real. It's perception of color by different people perceive the color differently because it's so narrow bandwidth.
So it's really mostly a problem with RGB lasers.
Yes. But even in our blue color, we add yellow light to that, or a portion of the red and the green into it to get to the right color point. So if you just looked at the pure blue, blue is less sensitive because your eye's not so sensitive in blue. The green is the worst, and then red. But there is that's one of the problems they have mastering at 2020 is two guys will perceive it, or people, I don't want to just say guys, but they will perceive that color different from the film. Film is not that narrow bandwidth, and neither is real world. So
right.
The color science works, but there's other effects. So think twice before you really want 2020. But I've seen stuff mastered at 2020, played back in Dolby Vision at 2020. Again, I think that's very early. They may get there, but there is the problem with people's perception on that narrow a bandwidth.
Did you see the movie Inside Out in
Unfortunately,
Dolby Vision?
I did not. No, I wish I did. I've seen a few Dolby Vision. It's an awesome setup.
It is an awesome setup, and the reason I bring up Inside Out in particular is most of the movie is in the P3 or DCI gamut, but there's one scene in the little girl's subconscious that they actually mastered in 2020, and it's kind of remarkable, actually. You know, you can sort of see the difference. It's also less bright, but it's also supposed to be dark and spooky, so that was okay. In the few minutes we have left, I would love to talk a little bit about high dynamic range and how it applies to projectors. We've seen it for years now on flat panel displays, and we're sort of in a nits war with flat panels, right? You want to get to OLEDs typically get to 500 nits. LCDs can get to 1,000. This year at CES, we've seen up to 2,000. The Sony Z9, there are a number of them that get super bright. Projectors obviously have a somewhat different problem because the amount of light that you actually see coming at you depends on the size of the screen, among other things.
Right. I mean, if you want 2,000 nits, you can do it, but it might be your 36-inch TV size anymore. But it depends on the
talk about what's old is new
projector.
Again. Yeah.
So the whole dynamic range that was developed around having a certain brightness and a contrast ratio for the black. And one thing you notice in the Dolby theaters is they're black, even with and actually those theaters are pushing, I think, 30, maybe 35. They were trying to get more, but you know, they're 2 to 3 times brighter than a normal theater.
Yep.
But the black level was 1,000 times better. You know, they're pushing 1,000,000 to 1 because of the way they're doing it. And that's the same way, you know, LCDs actually are either dimming the local area so you can get dimmer, or you can have 2 LCDs. That was the early approach, but that's very expensive. But they've gone to these LED arrays, or if you go to OLED, you can actually, it's an emissive device, so you can actually turn the pixels near black. Yeah. But on projectors, you have the light source on the imager all the time. So one way around that is to put another imager, or what we call dual modulation. And that's how the Dolby Vision works. It's been around a long time. We've had it in simulation and planetariums for many years. There's still products being sold in the simulation market and planetariums by now Rockwell Collins and Velvet through in Germany that make a dual modulation thing, but they're very expensive. They don't put out a lot of light, because if you modulate it a second time, you throw away half the light. They're not very efficient that way.
Yeah. We have a picture actually of dual modulation.
So this is one of the early ones. And basically you take a normal projector type input with the red, blue, green device, and it outputs through a relay lens. And normally that relay lens would be your projection lens, and you'd have RGB, and if it's a LCoS device, you could have 50, 100,000 to 1 contrast. If it's a DLP, maybe a couple thousand to 1. But if you put another imager in there, contrast is nice that it multiplies. So 100 times 100 is 10,000, or 1,000 times 1,000 is 1,000,000. They don't add; they actually multiply. So it's very easy to get 1,000,000 to 1 if you've got 1,000 to 1 contrast in each device, or the RGB and then the luminance channel. You could. It's not that difficult to approach 1,000,000 to 1, which is a very good black. Now you need to process it a little, but and it's a little difficult sometimes to get all the pixels aligned. as the manufacturers.
That is the trick, isn't it? Especially at 4K or even 8, or even worse, 8K.
Right. So it looks like on this one they're using an 8K for the luminance. So that's the other thing it brings up. You don't have to have the same resolution on the RGB as you do the Y value, because you could kind of like we have YPRPB, you can subsample the color, and in this case they're putting up 4 luminance pixels per 1 RGB pixel. So you could have a higher perceived resolution and still have the very high contrast, and not so expensive of RGB devices in here. So basically it's just putting 2 projectors in series. So you take one projector and output it back into the next engine, and then output that. And that's where you lose half your light, because you have to be able to turn it black. And that's, if it's a polarized system, you have to add another analyzer in there, and that analyzer becomes a polarizer for the Y channel. And you need some electronics in your signal processing and gamma control and things like that. But it actually works. Will this move into the home? That's a good question. JVC keeps pushing the contrast higher and higher in some of the dynamic approaches now. One thing, we have an advantage at JVC having very high native contrast. If you want to do a dynamic control like they do in the HDR, you don't have these multiple steps and see all the bouncing between the steps. We can move it without really seeing a big effect, because we still have a very wide dynamic range anyway. So the 4500 implements a lot of these new features to give a very good HDR black level and approaching
without using dual modulation.
Yes, because once you add that other modulator, it's a whole set of another optics, as well as the cost of the modulator. You have to keep it almost collimated, or you lose light there as well. It adds a lot of cost to a system. It can be done, but it's a cost issue.
Yeah, and as I understand it, that's how Dolby Vision projectors do it. They have a dual modulation, which lets them get down to that deep black.
Right. They
use
use a lot of lasers to pump it up to get the brightness
exactly
where they want to
be.
And maybe that's when it becomes viable in the home, because again, we talked about Aton Do and things like that. Until you get to laser doing imager to imager, the loss incorporated there is still quite a bit. Where if you actually could push laser to laser, then you would have more efficient. You still throw away half the light, but now you're probably throwing away 70% of the light, or 65, something like that. So
unfortunately, we're at the very early stages of high dynamic range with projectors. There are no specifications or standards for high dynamic range with projectors, are there?
No, and myself, I don't see that coming in the near term. The big markets, of course, the LCDs, and they can do that now with area array dimming. I think you get up 384 areas now, so you can dim a lot
more
of the
than
panel.
Yeah, I mean,
I didn't count the latest at CES this year, but I know they're just going crazy with the
number of local dimming zones. Yeah.
And so the more you get there, the less halo effect you have around the pixel. And so they're very good. And the number of projectors sold into that market is very small. So my prediction is you're going to have the various projector manufacturers figuring out how to handle the PQ curve, the HDR content, and they will apply their own magic based on their device and optics to give you their best rendition of what HDR is. It won't look the same as a panel. But you'll pick and choose your brand based on, how they implement it, just like we did with de-interlacing in the 1080i days, or other things in the past. Everyone's done it a little bit different and added chroma a different way, and this picture looks nice, I'll buy this brand. So we'd like to think with our native contrast, it gives us a bigger advantage over other technologies, just because we've got that to work with and don't have to overcome that with some other tricks.
Right. Well, it's certainly interesting times, and I want to thank you so much for being here and helping us understand projection technology. But sadly, we've run out of time.
Thank you, Scott, and the people that ask questions.
Yes, thank you very much. That's Rod Sterling, Chief Engineer at JVC. And of course, you can find out more at jvc.com. You can always find me at avsforum.com. You can email me at scott@twit.tv. And you can follow me on Twitter at htgeekscott and at avsforum. You can always find previous episodes of Home Theater Geeks right here at twit.tv and on our YouTube channel, youtube.com/twit Home Theater Geeks. Next week, my guest geek is scheduled to be home theater designer Theo Kalamarakis to discuss his latest venture in home cinema. So I do hope you will join me for that. Until then, geek out.